Our first speaker will be Dr. Andrew Costa, Associate Professor and Schlegel Research Chair in Clinical Epidemiology and Aging in the Department of Health Research Methods, Evidence and Impact, as well as the Research Director of the St. Joseph's Healthcare Center for Integrated Care. Following Andrew, we will hear from Dr. Victor Kuperman, Associate Professor in Linguistics and Languages. Our final speaker will be Dr. Ravi Selvaganapathy, Professor in Mechanical and Biomedical Engineering and Canada Research Chair in Biomicrofluidics. I will now turn the time over to our first speaker, Dr. Andrew Costa.
Thanks, Jazine, for inviting me and for introducing me. So, like many researchers on campus, certainly my program of research has shifted remarkably since the COVID-19 pandemic, and in particular towards doing new research that I obviously never thought I would be doing in long-term care and retirement homes. And before the pandemic, pre-pandemic, and still today, my team is 19 strong. We're the Big Data and Geriatric Models of Care Research Group. And we use large data sources, so-called big data, to design innovative pragmatic trials in real-world settings, as well as to do observational research, always focusing around the topic of integrated care. And I've asked many friends, and I've reflected on this, where were you when you first heard about COVID, or you realized that it would be the huge global pandemic that it has been? And for me, in fact, it was extremely memorable because I was far, far away mentally and physically from COVID. So I was in Cape Town, which, yes, actually is that beautiful. And I was at the University of Cape Town at the Albertina and Walter Sisulu Institute of Aging in Africa, working on some community programs. And being in the Southern Hemisphere, being busy on site, I was not following news. And I was there for a period of about 2 weeks, quite busy. And this was a very happy occasion for me because my family was to meet me there because my wife was born in South Africa. And we were going to spend some nice family time. So here's my daughter at a beach and sunset, Camps Bay in Cape Town. And so my mind was far away from COVID. And in fact, my wife, who had been following the news a lot better than I have, said, oh, there's this interesting pandemic emerging out of Wuhan province, the building of large-scale hospitals, et cetera. And I remember being distracted or just being so happy where I was that I said something probably very foolish. I forget what I did say. Basically saying that this is not going to be a big deal. You don't have to worry about it, which turned out to be obviously extremely foolish. And so as we went home very early in March, coming through the Paris airport, you could sense things were changing. And as I was reading news from the Paris airport to Toronto, my world had absolutely changed as an outlook for, what the next few years were going to be. I was reading epidemiological reports, seeing emails that I'd neglected for a week from colleagues in northern Italy involved in geriatrics, describing the horrible situations of the hospitals and indeed in long-term care and congregate settings for older adults. And already emerging was problems, terrible issues in retirement homes and long-term care facilities in Spain. And so everything had changed. And 3 large projects really resulted from this. For me, research in aging has always been sort of a personal story, and it emanated for me around the experiences of care that my grandparents had when I was growing up. And so it felt very personal, and so I dove right in. The first large project, which I never thought I would obviously be involved in, was due to a leadership role I have at the regional medical campus in Kitchener-Waterloo. There was a huge impact, a big bracing for local hospitals, a stockpiling of PPE, a real uncertainty out of what was emerging out of cases in New York and indeed what had occurred in Europe. And an awful lot of concern. And there was a huge need to join global forces like WHO to collect data on cases coming through the hospital, and a local need to do that as well to inform modeling, care, and just to know what was happening. So myself and Rebecca Crusobrink started a platform called Courage in Kitchener-Waterloo. Very quickly, this is sort of a hallmark of what occurred thereafter in very weird and wonderful ways. I was connected through Marla Beauchamp to Mylene Duong and Terrence Ho, who are interested in the same thing at Hamilton Health Sciences and St. Joe's. We collaborated to expand Courage as a multi-regional platform, which also has recently included the Niagara Health System, where we have detailed, up-to-date information on all cases coming through hospitals. And so really what we're doing is characterizing every bit of information we can pull out of the charts for individuals that are coming through hospitals. And work has been emerging in this for some time on a local level, as well as in publications as well, to look at presenting complaints, prediction of mortality, et cetera. And that was a hospital story. And we were very proud that we could actually take this hospital project and actually turn it into something that was actually a responsive platform for older adults, given that we knew that they would be the most affected by the pandemic. And really, as a result of the fears around hospitals being overrun, our long-term care sector and retirement home sector, long ignored, continue to be ignored, and was really sacrificed in terms of the time and resources that we put into preparedness in that short period in early March, and indeed into April. And so in the first wave, obviously, we've had well-publicized outbreaks in long-term care and retirement homes, and particularly long-term care, where the absolute risk of being infected with COVID-19, SARS-CoV-2, was about 7% in long-term care compared to about 2% in retirement homes. And we were seeing high case fatality rates of 27 and 20% respectively. And it was very interesting. Some facilities were spared and others had enormous, very devastating outbreaks. And that was true for long-term care and retirement homes. This was yet sort of another amazing thing that occurred during the pandemic in terms of new research and new research opportunities. The province started the COVID-19 consensus modeling table, led largely by the health data branch of the Ministry of Health. And previously, it's very difficult to get a hold of data, particularly person-level data, a very long and arduous process. But in this case, there was the need for expertise in long-term care epidemiology, which we had on the team, and the absolute lack of resources within the Ministry of Health to provide good consensus estimates on what was happening in the sector. So really a phone call at 10 p.m. at night with Michael Hillner, who's the ADM, and 72 hours later, we had research ethics and a data sharing agreement to pull in all the province's data on COVID related to long-term care and retirement homes. And our first work was to look at the profit question, given that it had taken up a lot of space in media, and we did that. What came out of that work was actually something very important that has influenced policy, which is the idea that long understood, long not understood, that there were a lot of facilities in the province that were actually from 1970 standards, and they were not upgraded over the years. This is again a classic example of how the sector has been neglected for so long. And in those facilities, which are not rare, obviously, there were large, devastating outbreaks, and to this day, they remain the single greatest factor to predict large, devastating outbreaks in long-term care. And so the work that we did actually is the provincial model for risk for long-term care and retirement homes. And this work continues to be taken up, including in the recent work of the Long-Term Care Commission in the province. We're also looking at policies pre and post lockdown, and in this case, for example, looking at how changes in connectivity between facilities has changed over time and what that means for future risk and risk ongoing. And so this work continues, oftentimes at the side of our desk and into late hours of the night. And usually when I'm working late at night, my wife will come and poke me and say, "I thought you said this was not going to be a big deal," which is funny, but maybe not nice. And we've engaged in new work in retirement homes where we're looking at spread factors funded by the Juravinsky Research Institute. And so this data about to be released looks at factors that predict the facility level outbreaks in retirement homes. And as this figure sort of cursorily demonstrates, we're seeing a large influence of ethnic concentration in the surrounding community as being important, which has been well publicized even before we released some of this work. And the work continues at the facility level. It's obviously just a part of the picture, and the experience of facilities is that outbreaks, despite best efforts, can sometimes get out of hand, and that has a lot to do with the insidious nature of the pre-symptomatic, asymptomatic period of COVID-19 and how we can't do a very good job at in our PCR test. We have huge false positive rates early on, false negative rates, excuse me, early on in the disease. And so Don Bowdish and I, with a very large team from McMaster, we're actually very well positioned at McMaster to do this, are looking at facility and immune level risk factors to examine risk and to obviously create change. This is new work yet to be announced, funded by the COVID-19 Immunity Task Force, where we're doing serological assays in 2,000 residents, all family members, and all designated essential visitors in 20 facilities across the province, with great support from partners and an absolutely massive team. And so for me, there were three learnings. Number one, it's important to know that a lot is at stake and continues to be at stake for older adults during the COVID-19 pandemic, and we're definitely not out of this as we see our protracted wave two. The silver lining was that what seemed impossible to achieve in research previously, the kinds of collaborations, partnerships, speed, is now possible. And hopefully these precedents will continue to drive progress in the space. I think we've seen a societal shift around thinking around older adults, living patterns, long-term care, and issues long ignored now I think will not be ignored. And progress now seems possible given that not only government is paying attention, but individuals and societies are now reflecting on their own aging course and how they want to age into the future. And that's it for me.
Okay, thank you, Andrew. Victor, would you like to click the share audio and video button and share your screen, please?
So apologies for this glitch. I'm Victor Kuperman. I'm presenting a project that started in 2019. And back then, as now, it had as its main subject loneliness, a social condition that affects about 30% of Canadians in the age bracket of 65 plus. Now, this condition is known to come with increased health risks, both mentally and physically. And what makes it particularly problematic for detection and addressing is that it's stigmatized. So not everybody is happy to say that they're lonely. And this leads to a common response bias in standard instruments like questionnaires. So our project meant to address this by changing a task. We thought we would ask our participants, the seniors, to write a story about a significant event in their life that happened in the past, or they envision it to happen in the future, or perhaps to also describe their present, their typical day. And we would look for linguistic markers of loneliness in these texts. So the technique behind it is common to natural language processing. We would use automated assessments based on word choices, topics, and text structure. And the goal was to develop a non-invasive screening aid, where we would ask a person coming to the office to provide a text on a certain topic, and we would predict the loneliness with some accuracy of that person and provide this information to practitioners which might find it useful. Our other goal was to develop a web-based tool for data collection and social engagement, where these stories could be written and shared. So 2019 went well. We received a MIRA Catalyst grant, which supported these activities. We collected data, both stories and loneliness data, from 350 participants. Even the very early steps of computational models, when we trained them, showed a non-trivial prediction accuracy. So based on words alone in the stories, we had a 68% prediction accuracy of how lonely that person feels. We developed an app that we called Writ Large, and this is the app that is available and in use even now. So we were pretty happy with our progress. And then, of course, the 2020 came and the pandemic came, and we realized that we had So first of all, we decided to use the same paradigm to study the dynamics of emotional state that the aging population experiences the focus of how they experience their present and their future outlook. We also can use our tools to look at the topics that elicit particular concern or give particular relief to people as they go through the pandemic. And the web tool that we have, the app, we wanted to strengthen it and made it into a stronger engagement tool to relieve isolation that, of course, the aging population experiences very drastically now. So we took the pre-pandemic data of 2019 and made it into the first test point of a time series. And since then, starting in April, May 2020, we've tested online a large number of older participants with, well, every 2 to 3 months we did that. The last such test point was in October 2020, and we already have one more planned in January of the coming year. And this, of course, was made possible by the LCMA COVID-19 grant. We've tested about 1,300 participants so far in Canada and the US, and some were tested twice, which gives us even more insight into a progression within an individual through the pandemic. So let me tell you a little about how we do it and what we find. So what you see in the left side of the screen is an actual text or part of the text that has been submitted online. And I colored it in the way that highlights positive words and negative words in green and red, respectively. And these are not the actual colors that we use. We use numbers that come from affective ratings that we've collected in our lab for a large number of English words. And these ratings allow us to estimate on average how positive or negative a certain story is, how anxious or arousing are the word choices in this story. And we can look into very many lexical characteristics of meaning with the tools, linguistic tools that we have. And we can do it per story, per participant, per testing session. And this gives us a pretty clear insight into the emotional state of individuals, both pre-pandemically and as the pandemic develops. And what I'll talk in more detail about is emotional reserve. The idea that in the face of adversity, we can keep our cool to some extent, we can maintain our optimism to a certain degree, but if the adversity is prolonged or harsh, we might deplete our emotional reserve and the optimism would drop. This is indeed what we saw in our data. What you see in the plot is on the horizontal axis, the future, the past, and the yesterday. These are the 3 topics that we asked people to talk about. We have positivity on the vertical axis, and each topic is represented by 3 points. And long story short, after 2 months of the pandemic, when we tested our individuals in April and May, they were as positive as they were pre-pandemically. So the emotional reserve still held at that time. The blue points that I highlighted here show a drop in positivity, and this is what we saw at 5 months after the lockdown was implemented in Canada and the US. And so this is what we take as a sign that emotional reserve is depleted or starts being depleted. And we see particularly strong drop in positivity in the future outlook. So the future is relatively bleak. We will track our individuals throughout the pandemic and hopefully after that, funding permitting. And we want to see whether the optimism will drop even more or whether at some point it will start bouncing back. Another aspect of the text that we can study using our data is the topics. So it won't come as a surprise that pre-pandemically, the most selling topic, the most diagnostic of this time, and the least diagnostic of the lockdown time is what we call vacation words. So this is a topic associated with ocean, island, canyon, boat, cruise, and so on. During the lockdown, a topic that is particularly strongly represented there, but not pre-pandemically, is represented by words like mask, wear, aisle, and so on. So what this allows us to do, these topics and many more that we're considering, this allows us to see what is at the forefront of the mindset of a person, both before the pandemic and as the pandemic develops. And again, we will track the trajectory of these topics over time to see how they change. The writ large app works. Right now, it collected data from about 1,000 contributors. We have about 3,500 stories. And it can be used both for contributing stories and for reading them. And so it's been advertised by newsletters and mailing lists, including MIRA and other partners. And we have a few organizations that are interested in customized versions that they would use to specifically collect data on the experiences, COVID experiences of their clientele. For future directions, we will continue our data collection throughout the pandemic, hopefully every 2 to 3 months, and we'll follow up even after the lockdowns are lifted and we're back to normal. We will continue to promote and improve the app. We're using focus groups and usability service for that because we get informal feedback that this takes the edge off of social isolation, the ability to read experiences from people who are in the same situation, the ability to write up your stories. This provides a event for the loneliness. And finally, we will make all data and tools public. We think this will become a unique document of the epoch. And I'm thanking my collaborators and, of course, the funding from MIRA and the Labarge Center.
Thank you, Victor. Ravi, would you like to click the video button and share your screen?
So thank you very much, and thanks everybody for the opportunity to present on our work. The project that we got funded from MIRA was on developing multi-tissue models for studying exercise and its influence on the brain. I'll talk a little bit about the project and its sort of genesis, as well as in the end how we pivoted basically for the COVID pandemic. So I'll start with a broad introduction. So tissue engineering is about using cells from a variety of sources, combining them with synthetic materials or with natural extracellular matrices, and then assembling them in three-dimensional fashion so as to make in vivo conditions of these tissues. There are a variety of applications for tissue engineering. It is used in drug discovery, where particular biological mechanisms can be simulated and then drug molecules could be tested. It could be used as in vivo bioreactors to produce certain hormones that may not be produced by the body for drug delivery purposes. And then in the future, it could potentially be used in making artificial organs for regenerative medicine. Lately, there's been a lot of interest in vitro modeling, where three-dimensional constructions similar to what we see in vivo situations can be assembled using newly emerging bioprinting and other additive manufacturing technologies to create in vitro models that can simulate particular disease processes. So there are various considerations for developing these kinds of models. The primary of them is that we want to simulate cell-cell interactions in an in vivo-like manner. We also want to provide the kinds of stimulation, such as, for example, mechanical stimulation in skeletal muscle tissues, or electrical stimulations, and so on, that can then lead down to certain biochemical pathways. We also want to provide three-dimensional interactions, very close interactions of various different cell types. And through these interactions, we want to simulate these kinds of signaling through the secretome of one cell to the other. And then in some situations, we want to simulate immune interactions between the different tissues that we're building and a blood-like solution that perfuses through them. So in this context, over the past 5 years, we've been developing several biofabrication technologies that can simulate part or some aspects of this requirement. One of the technologies that we have developed over the past year or so has been the self-assembly technique to create highly dense three-dimensional tissue construct. The way that we do it is we take a mold, such as what you see on the left image, that shapes the construct, and then into it, we put in a bioink. The bioink can consist of cells that we want to mold, as well as ECM, such as collagen and the nutrient media. And by the way that we exchange the media and the composition of this bioink, it quickly solidifies the collagen, then cross-links and forms a tighter network because it excludes water. And then subsequently, the cells attach to the extracellular matrix and then create tension forces within this construct that further tighten and make it much more rigid. Now, at this stage, it is quite handleable. And using our recipe, we are able to do this within a short frame of time, about 4 to 6 hours or so, as compared to longer several days in other systems. And because we are able to do it in a very short time frame, we are able to do things that are not possible otherwise. For instance, we can create heterogeneous constructs such as what you see on the right-hand side image, where we can put in different bioinks in different regions of this mold and create this heterogeneous composition where one part of that construct has a particular cell type and another part has a different cell type. So not only does this create highly dense three-dimensional construct, but it also allows the secretome of one cell type to interact with that of the other and then study these kinds of interactions. So what we then did was to test it out on a particular combination. Here we wanted to test the interaction between skeletal muscle cells as well as fat cells. So we used cell lines that that produced myoblasts and adipocytes, and then combined them in two different ways. One was creating a homogeneous mixture of these cell types and then casting them into these molds. The other was using our technique to create a heterogeneous mixture where we have one cell type in one end and the other cell type in the other end. And then what we found was that the response of these constructs to a drug molecule was quite different depending on the spatial arrangement or orientation. So what this provided us was a clue that the macro structure of how these tissue constructs are constructed, whether it is heterogeneous or homogeneous, is important in the kind of response that they provide for drugs. And we thought that this could be used in vitro modeling of disease processes. So then Ali Reza, who developed this technique, went on looking for collaborators, and we found Margaret's group was ideal for this purpose to implement this in a neuronal context. And he collaborated with Crystal, and we then brought together several other collaborators, both within McMaster as well as outside McMaster, in order to address this question where we wanted to develop an in vitro model that can mimic the effect of exercise on brain function. So this is where we have two different types of tissues, a skeletal muscle tissue and then a brain tissue, interacting with each other to then reproduce an effect that we see in vivo. And if you're able to do that, then we can use these kinds of models to then test effects of various kinds of stimulus that we can provide, exercise regimes, and as well as other drug interactions in order to look at this kind of a system. So for this, they combined cell type skeletal muscle cells with neuronal cells in order to create these kinds of construct. But they also then went on to develop a completely new biofabrication techniques where this kind of an interaction can be made much more defined and easier. And this technique is what we call as tissue in a tube model. Again, it's a very simple fabrication technique that can be used in a wide variety of labs. It consists of a tube that is gas permeable, and in it we then put in a couple of pins and then fill this self-assembling bioink. And when the self-assembly happens, it basically happens between these two pinning locations. And in that process of pinning, as these constructs shrink, the pins are also able to exert mechanical forces that then determine the way that this assembly happens. Through the pins, we can also then provide electrical stimulation. So this format allows us not only to provide mechanical, but also electrical stimulation. And then through the outer tube, we can perfuse solutions so that we can take the secretome of one construct and move it to another construct to mimic the interaction that happens in systemic circulation in the body. So what we were able to do was to develop these constructs, such as what you're seeing here. Through this simple technique, we can generate extremely large constructs. So the bottom figure that you're seeing on the left is a construct which is about 4 to 5 centimeters in length, which can easily be created in this particular fashion. We can also sequence and pattern the way that the different cell types are assembled one after the other, so that we can provide this kind of a heterogeneous construct and interaction between two different cell types, either in the axial dimension along the tube or in the radial dimension. And we have determined conditions where the constructs actually form without disruption, or conditions where they are actually, the tension is so high that they get disrupted as well. We've used this technique in order to build tissue in a tube models for fat cells, adipocytes. And here on the left, you see an image where we are able to get these fat cell lines to differentiate, produce enough fat molecules. We are also able to use this on skeletal muscle cells. And what we find is that with the appropriate kind of stimulation, we can create myofibers that are aligned along the direction of electric field. We've also used this to create neuronal bundles that can be covered through with a thin layer of endothelial cells in order to then mimic a blood-brain barrier as well. So that gives us the tool to then subsequently assemble these constructs through these pipings in order to then move the secretome of one to the other, and also size them appropriately so that we see the relevant effects that are needed. So that positions us quite well. We've also used electrical stimulation as a way to create these myofibers, and what we find is that we get these extremely long fibers depending on the way that we are stimulating them. And what we think is that using this kind of a stimulation, we would then be able to stimulate different kinds of exercises, high intensity exercise, moderate intensity exercise, or low intensity exercises. We find that these kinds of electrical stimulation play a big role in terms of other cell types such as osteoblast cell types, as well as neuronal cell types, in terms of the kinds of arrangements that can be created with this. So this is an area that we are continuing to explore as well. So this positions us very well in order to study the effect of exercise on the brain, and those are the kinds of assays that we are starting to do, and hopefully in the next few months or so we would be able to accomplish some of these things. In terms of the COVID pandemic, that has resulted, it initially resulted in basically stoppage of work. We pivoted, and in my group, a number of students helped in starting this initiative on protective equipment and materials, which is ballooned into a big research center at McMaster, helping produce PPEs or assist companies in producing PPEs. But in terms of this project, it has caused a number of issues. It has reduced interaction between students, eliminated travel to our collaborator laboratories in the United States. Again, overall reduced work hours, access to equipment. But more importantly, what we wanted to do was to acquire samples of blood from patients with Alzheimer's who had exercised and not exercised, and then use that as a level to then mimic models that could have similar secretome expression. We were not able to do that. So we are hoping to do this in the next few months. What we have focused on mainly was on development of the models and using levels in healthy patients as a way to standardize our models. And then what we're planning for the next year is to implement all of the other things that we had hoped to do in the past year. So that's the end of my presentation. Thank you very much.
I would like now to invite you to stay online and ask Andrew, Victor, and Parminder if they want to click their share audio and video button.
Great, Jazeen, thanks very much. Great presentation, gentlemen. It was very interesting to see the breadth and the diversity of talks this morning. And I actually wanted to take a moment to acknowledge, and I forgot to mention this earlier, that several of our International Scientific Advisory Committee members are also attending the Labarge Day. And there are a couple of questions that have come your way from the chair of the ISAC, which is David Hogan. And Andrew, I think there was a question for you, Andrew, from David, related to, could you explain crowding index? How is it calculated?
Well, what we found is that the number the average number of residents per room in a facility is highly correlated with a lot of other factors in a facility, like square footage, lack of distance communal space, shared bathrooms. And so, in fact, what we landed on was an extremely simple index, so simple that it's difficult to call it an index, which is just essentially the average number of individuals in a facility per.
Thank you. If there's a follow-up question, David, please type it in the chat and I can ask on your behalf. There was a comment from one of the poster presenters who asked me, Victor, question, perhaps you would like to consider the vaccine as a word appearing in your analysis in prime 3 and 4 and 5, and how that affects emotional reserve as well. That's just a comment. Another question from David Hogan to Victor. Does the affective ratings award vary if the person is talking about themselves or others? Interesting question. Victor? Oh, Victor is frozen. Maybe I'll come back to Victor a little later. And there's a question from Stuart Phillips to Ravi, and that is, have you ever used a human progenitor cell in your model?
Yeah, I mean, that's a great question. And that is the path that we want to go to. The cells that we're using are neuroblastoma cell lines. They're well understood, and therefore we started with something like this. And typically in a model, what we want to do is to mimic at the early stage what is known, and to show that the model can actually reproduce some of these things, and then subsequently go with more interesting cell types, I would say. So that is another area. Brain organoids, for example, and cells from that is another area that or cell types that we can use to assemble. And there, what we would find is things we may not necessarily be able to compare with what is there in the literature, because the literature there is also sort of coming up and growing in these cases. So I mean, the technique, we started with the technique because it's a nice way to engineer the kinds of shapes and structures that we want. The main difference, though, here is that this is an assembly technique rather than growth technique, right? And in the body in vivo, you have growth happening, where these factors then trigger the formation of macrostructures and so on, which we are artificially creating it in an engineered structure. And that's an interesting question to study. Is there a difference, or does it make a meaningful difference when we are doing drug testing, for instance, right? So those are all sort of the questions that we want to address first, and then move on to
Thanks, Ravi.
the more interesting aspects.
Victor, there was a question from Dr. David Hogan. Does the affective rating of words vary if the person is talking about themselves or others?
Yes, I apologize. There was a connection problem on my end. So to this question, we don't know of any systematic differences in this dimension, but there is a difference when a person is talking about their own group and some other group. So it's us versus them. Us, of course, are more positive.
Maybe in the interest of time, we will move on. Victor, maybe you want to type
in very different ways, age-wise or nationality and so on.
Victor, if you don't mind,
can I answer the previous question as well?
Send a response in the chat box. That would be good. Much appreciated. There's another question from David. Ravi, have you specifically examined the interplay of cells that compose the neurovascular unit?
No, we haven't, and that is definitely an area of interest. And one of the collaborators on the team is Scott Canfield in Indiana, who has particularly looked at the neurovascular unit and has the right cell types. And part of this collaboration was to for the student to actually go over to his lab and actually get trained and bring that information and knowledge back over here so that we could use our technique and share our technique with that lab as well. So one of the key effects of the COVID has been that was not possible, and hopefully in the coming year that would be possible to do.
Ravi, I have one question. As you were creating methodology and tool that the group is creating, I was trying to think about, in the sense of what MIRA does or what LCMA is being engaged in, how do you see the application of this in relation to improving mobility, let's say, or other outcomes that might be of important to the older people?
So what we think and where these models could help is first to understand the systemic effects, right? So what is happening with exercise and its influence on the brain itself. And then if that is proven and well established in the model, we can then use combinations. So these are engineered constructs, and we can impose sort of conditions and then look at understanding what is actually happening in the body in a more vivid detail, right? So because we can actually visualize what is happening within these constructs and where the action is taking place, which is not necessarily possible in an in vivo, either in animals or in humans. And therefore, this could promote greater understanding, and it could also have a directed experimentation in combination of drugs with exercise to then enable even older adults who may not necessarily be capable of doing those exercises to be supplemented to enable healthier lives, right? So that's where I see the effect, the long-term
Thanks. In the interest of time, I will ask one more question. There's a question from Margaret. Andrew, can you use your data to make specific recommendations on government standards, for example, bed density, staffing / patient staff, etc.?
Not precisely. You know, that's a great question. One of the limitations in our data and the limitations of the data in the sector is that we don't have good numbers on staffing because it's held within facilities, and so we don't know. But it's absolutely the mediator of infection. It's the mediator of quality, and so even though it's not oftentimes reflected in our data, although it might be in the future, it's definitely the largest factor we can all agree on among researchers in the sector that needs improvement. And so in terms of ideal staffing ratios, that's not a matter of current research. Ideal is certainly more, and it's absolutely the case that we're far from the ideal.
Great. Thanks, Andrew. I want to take this opportunity to thank all of our 4 speakers. It was a great wide variety of presentations, interesting topics, and it sort of ranged from how basic science is dealing with some of the challenges that we have in front of us to study the health and health of the older people. Andrew's talk looking at how research during COVID can inform public policy if we have access to the right data at the right time and where the opportunities lie. And Victor's presentation is a very interesting presentation in the sense that it gets us into the minds of the people, what they are going through during this period. And it will be interesting to see how the people's language and stories continue to reflect what they have gone through over the 8 to 9 months, and whether it becomes part of their life story. So I want to thank you very much for presenting today.